In this talk, I want to take you on a hopefully entertaining, unusual journey, which meanders somewhere between seismology, musicology, acoustics, ethnology, and computer science. For me, this journey started 14 years ago, when I discovered singing. It is not that I hadn't been involved with music before, on the contrary. Music has always been an integral part of my life. I even studied musicology at the University of Tübingen for 2 years. However, my previous musical activities had mostly been related to instrumental music. It turned out that starting to seriously engage in singing affected not only how I spent my free time, but also my research activities. Because pretty soon I became interested in singing also as a research topic. One thing led to another, and a few years later, I found myself being co-PI of a research project on traditional Georgian vocal music, which ran until a couple of months ago. But the story doesn't end there. Very recently, Reza Esfahani and Zara Zali, the last 2 PhD students which I co-supervised, finished their thesis on seismological topics in which they used advanced concepts from the field of music analysis as key tools of their work. And this would definitely not have been possible if I would not have become interested in singing. So for me, singing had a lot of unforeseen side effects, directly and indirectly. And in this talk today I will focus on the direct side effects, and I will try to demonstrate that singing can be an interesting research topic for seismologists. One of the reasons why Reza and Zara could so successfully exploit signal processing tools from the field of music analysis in their seismological research is the fact that seismic and acoustic waveforms have many properties in common. They even look similar if you stretch or compress the time axis properly. To illustrate this visually, I'm showing here 5 waveforms, 4 of which are of seismic origin and 1 that is not. Visually, it's hard to tell the difference. Acoustically, it's very easy.
Mary had a little lamb, its speed was quite as slow, and everywhere that Mary went, the lamb was sure to go.
What you've just heard is one of the first recordings of a human voice, namely that of Thomas Alva Edison from the year 1877. This similarity of seismic and acoustic waveforms has fascinated me for a long time. And because of this similarity, and because the Earth vibrates continuously, it can also be analyzed from a musical acoustical perspective, in other words, as a musical instrument. I have used this perspective quite often, both in scientific and non-scientific contexts, particularly related to outreach activities in schools, museums, and the like. Today, however, I want to show that this reframing, as the psychologists would call it, also works in the opposite direction, namely that musical instruments, in the present case the singing voice, can also be approached from a seismological perspective. My strong interest in singing started with my encounter with traditional Georgian music. I'm not talking about Georgia in the US, but the country in the Caucasus, located on the border between Europe and Asia. And here we are looking at the high mountains in the region of Svaneti, in the northwest of the country. Georgia, which is just the size of Bavaria, 70,000 kilometers squared, has a remarkable diverse musical tradition. To Western-trained ears, this music often sounds unfamiliar because the used tuning systems do not fit into the familiar scheme of major and minor tuning. Traditional Georgian multi-voice singing has fascinated musicians and music lovers for a long time. Many people have tried to put their fascinations for this UNESCO's World Cultural Heritage into words, but few manage as well as the cellist Slava Rostropovich. I let you read this for yourself. Another enthusiastic praise for this music comes from the composer Igor Stravinsky from an interview in 1966. And even today, there is still a good chance to experience Georgian singing in a traditional context in some villages outside of Tbilisi, in particular during a so-called supra, a traditional festive meal. During a supra, which can last for many hours, sometimes even days, people eat, drink and toast a lot. And often a toast will be followed by a special song. And one of the songs which might be heard in eastern Georgia, if the singers are good, is the following. What you just heard was the beginning of Shakrulo, a so-called table song, in this case from eastern Georgia. This, by the way, is one of the 27 pieces of music which have been sent into space on the golden record on board of the Voyager mission, which was launched in 1977. Well, my first encounter with traditional Georgian vocal music was at a singing workshop of Frank Kane, an American voice teacher living in Paris and teaching traditional Georgian vocal music, a rather unusual combination. Frank, who became my first teacher in Georgian singing, believes that body vibrations generated during singing are an essential part of Georgian vocal music, and he uses them in his teaching in a number of different ways. In one of the early workshops which I attended, he asked the participants to try to sing into their body and try to feel the corresponding vibrations in their knees. At first I thought that this might be some sort of educational image. Voice teachers can be very creative in this respect. It was this particular exercise which initially triggered my seismological curiosity. So after the workshop I told Frank that I would be interested in trying to measure these vibrations and asked him if he would be willing to take part. He agreed, and from there on we jointly started some, I would call, seismologically inspired experiments. Partly, like here, in a sound studio together with Wolfgang Loos, a professor at the University of the Arts in Berlin, and some of his sound engineering students, to quantitatively investigate the generation of body vibrations during singing and their properties. We wanted to find out if these vibrations could be measured, and if yes, what their properties are. Of course, I also searched the literature. It turned out that the first experimental work on body vibration measurements related to singing had been done already in 1875 by Etienne Jules Marais in France. During the second half of the last century, the interest in this field seems to have been rather strong in the group of Johan Sundbeck in Stockholm, but with the exception of the PhD work of Tori Takada in Hamburg, not much related work has been going on in the recent past. This is in contrast with other fields of science and technology, for example, medicine or communication. In Japan, for example, people tried to exploit body vibrations in form of non-audible murmur for silent mobile phone communication. But due to the lack of public interest in this technology, this research has been abandoned by now. So one of our initial challenges was to find out what kind of instruments to use. Since my prior experience as seismologist was with big geological bodies and big sensors, Daniel Vollmer and myself experimented quite a bit with small vibration pickups used for musical instruments until we finally settled for so-called larynx microphones, which pick up the muscle vibrations close to the larynx. These sensors, designed for speech communication in very noisy environments and used by firefighters, helicopter pilots and the like. It soon became obvious that body vibrations during singing can be recorded all over the body. Here you see spectrograms for the recordings of a singer taken at different positions of the body from head to toe. We can see that with respect to the spectrogram of the regular microphone signal framed in red, high frequency information, which is shown in the upper parts of the spectrograms, is increasingly lost if we go away from the neck region. But even at the ankle or the toe, we see some spectral structure in the low frequency range of the body vibration signal. Actually, with a bit of effort in terms of coupling, we were able to obtain really nice high fidelity recordings down to the ankle, which clearly captures the fundamental frequencies of the voice and their temporal changes, in other words, melodies, as well as the overtones up to 3 to 4 kHz. The higher overtones seem to have been damped out during propagation from neck to ankle. In order to learn more about the propagation mechanism, I calculated the phase delay between the neck and the ankle recording and the corresponding propagation velocity. This suggested that one of the obvious propagation mechanisms is through the bones. With my growing interest in Georgian music, my dormant interest in musicology was reawakened, and I began reading every research paper on Georgian music in English which I could find. I also went to Georgia several times for singing training and for a symposium on traditional polyphony in Tbilisi, where I got into contact with ethnomusicologists. That was when I began to learn how these people actually work, in particular in the field. What you see here is the kind of recording setups which traditionally have been most popular in ethnomusicological fieldwork. And in the top left panel you see Karl Stumpf and Georg Schünemann from the Berlin University recording prisoners of war, of World War I, of course, with a phonograph. The photo was taken in a prisoner of war camp in Frankfurt Oder. And in the right panel, ethnomusicologist Francis Densmore is seen to record a Blackfoot Indian chief, while in the lower left you see Simcha Aram with pygmies in Central Africa. So what is recorded is usually just sound, and more recent maybe also video. Subsequently, trained ethnomusicologists listen to these recordings and transcribe the individual voices according to what they hear into a Western notation system. Here you see an example for such a transcription taken from a paper by ethnomusicologist Susanne Ziegler from the Ethnological Museum in Berlin. There are several problems related to this. The whole approach to transcribe non-Western music into a Western notation system is fundamentally flawed. The tuning system of non-Western music can deviate considerably from the Western 12-tone equal temperament tuning system on which our pianos are based. This is usually accounted for by the transcribers through special signs, little arrows, for example, which are used to quantify the deviations between what they hear and what they can represent in Western notation. To separately hear the individual voices and to recognize their corresponding pitches from field recordings is extremely challenging, even for well-trained people. And it always remains subjective, in other words, an interpretation. What is especially tricky is the transcription of ensembles. No matter what you do, there is a trade-off. If one records individual musicians in isolation, this was, by the way, already done by Karl Stumpf in 1900 in the first phonograph recording session for the Berlin Phonogram archive shown here, one can nicely hear and analyze individual musicians. However, what is lost completely in this setup are the effects of the interaction between the musicians. On the other hand, if one records the whole ensemble together, the natural interaction between the musicians is maintained. But it becomes difficult to recognize the contributions of the individual musicians. Interaction between the musicians, however, can be essential aspects of a performance, in particular for a cappella vocal music. So when I first learned about these transcription issues, I thought very naively, why not computationally determine the pitches from the audio recordings of the whole ensemble? It turned out, however, that as of today, pitch recognition from audio tracks only works really well for single voices yet. And for every idea I came up with, it turned out that there were compelling counter-arguments. Close-up microphones wouldn't work either because of unavoidable crosstalk, and solving the voice separation problem as a classical inversion problem turned out to be too underdetermined. So at some point, I don't remember exactly when this happened, it occurred to me that maybe we should forget about audio recordings and try to use the recordings of muscle vibrations for pitch analysis. So I decided to test this idea. In order to be useful for transcription, the larynx microphones would need to meet two conditions. First, they would need to solve the voice separation problem, in other words, be insensitive to crosstalk, and second, larynx microphone recordings would need to contain sufficient information about the pitch of the voice so that monophonic pitch tracking algorithms could be successfully applied. An additional challenge was that I needed to get a special type of singers for my test. Since I wanted to make the crosstalk test as hard as possible, I thought to use a singing style in which the individual singers explore a large dynamic range and which contains rapid changes of the tempo. And the best singing style in that respect which I could think of was yodeling. And I thought if the idea would work with yodeling, it would work with any music. Fortunately, Berlin hosts a very strong yodeling community. A related problem is to test the quality of pitch determination algorithms. This unfortunately is not as easy as it sounds. Although pitch has the unit of hertz, it is not a physical but a psychoacoustic quantity. It is generated in the brain by combinations of processes which are not completely understood yet. Only in case of simple sinusoidal tones, as they are, for example, generated by a tuning fork or in a computer, are the signal frequency and the frequencies recognized by a human listener as pitch identical. So in order to test if a pitch tracking algorithm works properly, one usually generates synthetic pure tone audio signals which are generated based on the numerical pitch values, here written as f of t, generated by a pitch tracker. Now the original and the synthetic can be compared acoustically. With headphones, one can listen to the two signals simultaneously, one on each ear. If one doesn't have headphones, one has to listen to the two signals sequentially. And that is what we will do. You will now hear a short performance of the trio La Vache qui crie with the Bücheljutz from central Switzerland. And subsequently I will play back to you the synthetic pure tone signals so that you can compare the results of the pitch tracker with what you heard before. Here you see the visual results of the pitch tracking algorithm applied to the larynx microphone recording for singer 1. The black wiggly lines indicate the pitch trajectories of the fundamental and the overtones as captured in the neck vibrations. The blue horizontal bars correspond to the recognized note objects. Now let's listen to the pure tone signal for singer 1. To my ear, the synthetic note trajectories capture the original melody of singer 1 nearly perfectly, except for short artifacts. The same is true for the second singer. As well as for the third. in contrast, you can see and hear what happens if we try to track the pitch from the recording with a directional microphone. It's essentially useless for any automated subsequent analysis. So the voice separation worked extremely well in this experiment, and the reason is fairly easy to understand from a seismological perspective. Crosstalk happens because acoustic waves from one singer propagate through the air to a microphone of another singer. The larynx microphone, however, picks up the muscle vibrations close to the larynx, which get there from the larynx as elastic waves. So as long as we can prevent the larynx microphones to pick up acoustic waves, which can be done by construction of the outer shell of the sensor housing, there will be no crosstalk. So conceptually, using body vibration recordings corresponds to reframing the acoustic recording of a singer as a seismological observation problem of elastic waves. So looking back, it becomes obvious, and it's surprising that this has not been utilized earlier. There were some additional lessons which we learned from this experiment. The comparison of larynx microphone recordings with conventional audio recordings also showed that body vibration recordings contain all the essential information of a singer's voice regarding pitch, intonation, and voice intensity, but offer the additional advantage that they are practically unaffected by the voices of the other singers. The consequences of this property are rather far-reaching. Since computational analysis tools for monophonic voices work very well, using body vibration recordings of singers opens the door for a quantitative and reproducible analysis of the contribution of each singer while they are singing together. You can imagine that realizing this was extremely exciting because it made a long-standing observational problem in ethnomusicology essentially disappear. One question that remained open at this point in time, however, was if it would also work in the field. Would singers in the mountains actually let me tie this kind of equipment to their necks and let me record them with it? So, in order to find out, I went to Georgia for a feasibility study in 2015. The year before, I had met Nana Mjavanadze, a Georgian singer and ethnomusicologist who at that time was still working on her PhD. I took a multi-channel audio interface with me, a couple of larynx microphones, and a very basic video recorder. Our target region was Svaneti, in the high regions of the Caucasus Mountains, essentially at the border to Russia. Nana knew the music, the area, and the people very well, and was able to set up all the contacts to local village singers. Svaneti is a very fascinating place because it is one of the rare regions in the world where very old and presumably pre-Christian traditions, such as animal sacrifices, for example, are still cultivated as part of daily life. Songs from Svaneti, as part of Swan rituals, therefore occupy a special place within the Georgian music, since presumably the first stages of its development have been preserved in them. A total of 10 singers in 3 villages were willing to take part in my 2015 experiment and have themselves recorded in 4 different trio combinations with larynx microphones tied around their necks. Here you see 3 of the singers which we met and which I could record. This is a picture of the first recording session with Islam Pilpani, Gigo Chamgeliani and Murad Pirzghalani from Lenjeri and Lakhushki respectively. Islam Pilpani used to be a very well-known singer and the longtime leader of the ensemble Riho. Unfortunately, Islam and Gigo have both passed away since this recording session. You can see the praise for the larynx microphones around their necks. Let's now listen to the audio recording. As I said already, this was a very simple ad hoc experiment, so the video equipment which I had available at that time was very poor, but I simply took along what I had. You will hear the beginning of the Swan song Elia Lirde, which starts out with a short monophonic introduction by the lead singer, followed by a polyphonic part. Elia Lirde, This figure now shows the pitch and note trajectories for Islam's voice. The blue horizontal bars again correspond to the recognized note objects. The yellow shaded part in the right portion of the panel corresponds to the polyphonic part of the song. So when I start the playback, you will now hear the larynx microphone recording of Islam, so not the synthetic signal as before. The question is now simply if the separation of Islam's voice from the other two singers' voices works as expected. So please pay particular attention to the transition between the monophonic and the polyphonic part, when the two other singers join in. You could hear that the body vibration record is absolutely clean. Despite the fact that all of the three singers sang very loudly, the larynx microphone recording which we just heard only contains Islam's voice. So it turned out that using body vibration sensors to record singing voices provides a surprisingly simple solution to the source separation problems for the recording of vocal music even in the field. I should add, under the condition that one wants to use these recordings for subsequent computational analysis. These recordings are not aesthetically as pleasing as audio recordings, but they can directly be used for automatic pitch recognition and note estimation with high precision. This fact, and this cannot be overemphasized, allows the analysis of the contribution of each singer together with their interaction, while they are singing in their natural singing environment, sometimes in close body contact. We will now look very briefly at some of the properties of the larynx microphone signals and what they can be used for. First, as I mentioned already several times, the computational determination of the pitch tracks of the individual singers now becomes straightforward and requires essentially no additional pre-processing. I spare you the technical details here. So the blue, red and black traces correspond to the pitch trajectories of the top, middle and bass voice singer. You can identify the monophonic introductory part of Islam singing the middle voice, followed by the polyphonic part. The vertical axis is in cents, a unit commonly used by ethnomusicologists to measure relative pitch differences. As a reminder, 100 cents corresponds to one semitone, 1200 cents to an octave. You can see that the raw pitch trajectories look very noisy, and the reason is that the larynx microphone does not only pick up stable pitches when the note is sung, but also everything else which is happening in the laryngeal region, which causes the muscle to vibrate, clearing one's throat, swallowing, and the beginning of an intonation, even if it's not audible for other people, if it's not amplified. However, it is fairly easy to computationally isolate only the stable regions of the pitch tracks. These are the sound segments which we perceive as notes, which then become clearly visible. Of course, the lyrics were manually added to the output file. So this actually is an unbiased representation of what the singers were singing during that recording session. Larynx microphone recordings can also be used to calculate a number of interesting acoustic properties related to physical models of consonance and dissonance, for example. One of them is called sensory roughness. The reason why I show this here is not to go deeper into the theory behind this model, but to confront you with the name of one of the pioneers having worked in this field, Leon Nopov. The seismologists will know Leon Nopov as a highly decorated geophysicist, one of the pioneers of theoretical seismology. He was a professor of geophysics at UCLA, but at the same time held a research position at the Institute of Ethnomusicology, the name of which is usually related to Charles Seeger, the father of Pete Seeger. This land is your land. The older of us know this song. So he was also one of the pioneers of computational ethnomusicology long before this name was even used. But let's get back to Georgia. The pilot project was extremely successful. It confirmed under field conditions that already during the recording, the voices of the individual singers can be separated well enough so that the resulting signals can be directly analyzed using algorithms for monophonic signals, essentially without any time-consuming pre-processing. So to make a long story short, after being back in Potsdam, I applied for a leave of absence to do additional fieldwork. This seemed very urgent, since the village singers who had still learned their music by oral transmission were already fairly old, and it was not clear how much longer they would be around. As I said before, only one of the 3 singers of Elielöde is still around today. The university president was supportive, and in 2016 I went back to Georgia for a 3-month field recording project, again together with my Georgian colleague Nana Mjavanadze. Here you see the locations of the 25 recording sessions which we recorded during that experiment. Since we wanted to study the oldest layer of the Georgian music, our emphasis was still on Upper Svaneti. And as a consequence, the vast majority of the recordings involved Swan singers or people performing Swan prayers, either in Svaneti or in Swan settlements outside Svaneti, like Didgori, Tsalka and Udabno. However, we also used the opportunity to record a few groups from other regions. And based on the lessons learned in the pilot study, we now use the professional recording equipment, which consisted of high-quality DPA microphones, larynx microphones, an Olympus stereo recorder for the room recording, and a high-quality video camera with a directional microphone on top of it. And we came back with a total of roughly 250 sets of different recordings of folk songs, religious hymns, funeral songs, prayers, and lamenting. According to common fieldwork standards, each recording session was also accompanied by detailed interviews with the musicians done by Nana. To give you an idea of the kind of material we collected, I let you listen to the beginning of a women's song recorded in Udabno, close to the Georgian-Azerbaijanian border. These women are so-called eco-migrants, which have been relocated by the government in the 90th of the last century after their village in the mountains had been destroyed by rock avalanches. For the sake of completeness of my story, I still have to mention another twist to it. In 2015, so 1 year before the big field expedition to Svaneti, I was participating in a meeting of the International Society for Music Information Retrieval in Malaga, which is like the AGU meeting for computer scientists interested in music processing, to learn more about this rapidly evolving field of research. During one of the evening concerts, I happened to sit right next to this man, who turned out to be Meinhard Müller, one of the world's leading experts in the field of music processing and the author of the standard textbook on this topic. This meeting turned out to have a lot of consequences. And the trigger for these consequences was this man, Artem Erkomaishvili, one of the last master chanters of Georgian liturgical chant, who passed away in 1967 at the age of 81 years. In 1966, 1 year before his death, Artem Erkomaishvili was asked to perform a series of chants to save them for posterity. This had to be done sort of in secrecy, since chanting was prohibited during the Soviet period. However, he had no fellow singers to sing with him. They all had passed away already. Therefore, he had to sing all 3 voices by himself. This performance was recorded at the Tbilisi State Conservatory using 2 tape recorders, which were subsequently operated in what is now called overdubbing. When I had come across Artem Erkomaishvili's recordings, I thought that because of the special recording setup, it might be possible to separate the individual voices with a simple sequential deconvolution technique. The results of my attempt seemed, I would say, promising, but were not very impressive. This was the time when I remembered my meeting with Meinhard Müller in Malaga. I sent him a long email, explained the problem, and asked him if he had an idea how to solve it. Not only did he have an idea, he also had a brilliant student, Sebastian Rosenzweig, who solved it very nicely in his master thesis. This was the beginning of a collaboration which first resulted in the generation of yet another unique dataset of recordings of polyphonic music for which we had been able to solve the voice separation problem. So in early 2017, we were sitting on an absolutely unique data collection of several hundreds of audio and also video recordings of traditional Georgian vocal music for which we had separate tracks for each voice. For our fieldwork corpus, this was achieved by using larynx microphones, and for the Erkomaishvili dataset by, sloppily speaking, reversing the sequential recording strategy, the overdubbing. Originally, I had no specific plans what to do with all the material. The whole project had started from this, I would say, crazy idea to measure the body vibrations during singing. Then, purely driven by curiosity and the enthusiasm for the music, one thing led to another and affected my whole research. By 2017, part of me had become some sort of self-taught ethnomusicologist. I had read probably most of the English research papers on traditional Georgian music, and I had become aware of most of the relevant musicological research questions in that field. In addition, during the joint fieldwork with Nanam Javanadze, who has also been my singing teacher for many years, I had realized that the special properties of our data collection might suggest solutions to some previously unsolvable research questions. For example, if there is something like a Georgian tuning system. In addition, the collaboration with Meinhard Müller and his group during Sebastian's work on the Erkomaishvili recordings had been extremely stimulating. So at some point, we started to think about writing a joint proposal to the German Research Foundation to ask for funding to further explore some of our ideas. And the result was the research project Computational Ethnomusicology of Traditional Georgian Vocal Music, GVM, which, against all odds, since I represented the musicological part in it, got funded and which ran from 2018 until the end of 2022. And the Potsdam part of it is probably the only ethnomusicology project ever run from an Institute of Geosciences. Although, as the example of Leon Nopov testifies, I'm not the first geophysicist to work in this field. In terms of involved disciplines, this has been the most diverse project of my whole professional life and an incredibly enriching experience scientifically as well as personally. What I've tried to show in my presentation is that by reframing the recording of the singing voice as a seismological observation task, the source separation problem in ethnomusicological fieldwork, which is more than 100 years old, has a surprisingly simple solution in connection with subsequent computational analysis. Body vibration recordings are perfectly suited for computational analysis of singing voices while the singers sing in their natural environment. And the analysis of body vibration enables the use of new analysis methods and new digital representations, for example, visualizations of non-Western vocal music. And for me personally, computational ethnomusicology has turned out to be a fascinating research field, which is methodologically actually not very different from seismology. And as the PhD thesis of Reza Esfahani and Sarah Salih testify, I believe as seismologists, we can benefit a lot from the concepts and tools from audio processing. So in the course of working on the Georgian Vocal Music Project during the last 5 years, we were able to touch upon a number of different research topics, each of which is fascinating for a different reason. Since this is a sort of geoscience seminar, and since I do not know if the purely musicological aspects of the GVM project are of interest to you, I stop here. The story up to this point covers the essence of what I promised in my title, a seismologist approach to the analysis of Georgian traditional vocal music. If you're interested in any of the musicological topics, the latest issue of the journal German Research of the German Research Foundation contains an overview article of our project, with links to additional resources, which, however, you can also find on the Soundscape Lab website of the University of Potsdam, shown here. Finally, I want to acknowledge the contribution of all the people who supported this unusual project along its way. The list is too long to name them individually, but this project ran against many obstacles. In the end, it always worked out magically. Most of all, I feel indebted to all the singers from Georgia with whom I had the pleasure to interact with and who taught me that tradition does not have to be the worship of ashes, but tradition can also be the preservation of the fire, in slight modification of this quote of Jean Jaurès. In this sense, Didi Madloba, thank you very much.